Yep. So, hello everyone. So I guess we are live. If I can get some comments, like, am I audible? And are we visible, both Swamber and me? Am I audible, guys? Yes. Okay. So there are two yeses, and we also have Akash in the live, I guess. So that's great to have Akash. So guys, welcome to the machine learning session, the first machine learning session of this tenure. So this year, our ML lead Swamber is going to take ahead the session with, and I would not waste much of a time. I would say that this is a pretty basic and introductory session, and I guess in ML most of the peoples are concerned about building models and getting good accuracy and precision, but the base needs to be strong, because I myself remember, and Akash can also like join in the comments and say that the only question that we had asked in ML interviews was, what is the difference between linear and logistic regression? And most of you guys are still confused that which one is a regression model, which one is a classification model. So I guess that this session goes well. And yes, Akash is there. Okay. So please be interactive. Swamber is here to answer all your doubts. There will be certain hands-on things that will be shared in the live comments. So there are notebooks, there are stuff which are prepared for you. Google Colab Notebooks. Do also engage with them. And if you have any doubts, ask Swamber, and hopefully it's a great session and you guys enjoy it. So that's all. Over to you, Swamber.
All right, hello. I hope I'm audible, everyone. Can I get some reply? Hello, am I audible? All right, I see some replies. Okay, so um, first of all, welcome everyone. My name is Shoyambar Rai Chaudhary, and I'm from the GTG on campus Heritage Institute of Technology. And this is going to be our first session. So in this session, we are going to learn some basic stuffs about what machine learning is all about, how is it different from AI, and what is the difference between data science and machine learning. And along with that, since the name suggests think linear, we are going to learn about some linear models, and we are going to implement with our own Python class. And yeah, so we have something ready for you guys. So let's start. So the PPT is on the screen, right? So, so as the name suggests, think linear. We are going to start from the basics and move till multiple linear regression model. We are going to derive all the equations um, in a notepad and share with all of you. And yeah, so the first slide, what is machine learning? So as you can see, the Venn diagram is given. AI, machine learning, deep learning, and somewhere in the side we have data science as well. So as we can see, AI is the umbrella term covering all of the machine learning and deep learning segments. And well, what is AI? As we can see, artificial intelligence, it suggests that we provide machines the ability to mimic human actions, like providing them with human intelligence, and so that they can perform tasks like decision making, logical reasoning, and a lot of human like actions which we do. But coming to machine learning, which is a subset of AI, machine learning focuses more on learning from the past. Uh, well, I should not generalize learning from the past, but yeah, learning from the past would be a better way to describe what machine learning is all about. So we try to see a lot of data and we try to learn from those data and learn the rules from the data, and we provide answers uh, like we can say for traditional programming, think like you are given a lot of data, and you somewhere can write if else conditions, and you can provide that if your age is lesser than 18 you cannot vote, and if your age is over 18 you can vote. But this was simple because we had two conditions. But if there are multiple conditions, those nested if else would look gigantic. So we cannot write nested if else that much. So what we do in machine learning is we see the data and we see their answers or the labels. They are oftenly known as labels, and we try to create those rules. Okay, so we kind of find a mapping for those data to their answers, and we try to find the mapping and perform the function, which is like this mapping is known as creating a function of the input, which is the data, and we figure out those rules, and this is how we make uh, machines learn from past data. So I guess I'm clear about what is the difference between machine learning and traditional programming, right? Uh, okay. So types of machine learning. So machine learning can be broadly classified into three types. The first one is supervised. The second one is unsupervised, and the third one is reinforcement learning. Now, reinforcement learning is a very advanced topic. So we are going to speak very brief about what RL is all about. So supervised learning, let's come to supervised. So supervised, as the name suggests, it supervises you. That is, the data, in that data, you'll be provided with labeled data. What do you mean by labeled data? Labeled data is that you have an output column, might be one or more than one, should be one actually. So you have output column which is labeled in such a way that you can predict that for this given input, this should be the output. So your past data looks like for this given input, this is going to be the output. This is supervised learning. In unsupervised learning, there is no labeled data. That is, you are just given input and you don't have any output. So what you need to do is you need to cluster the data, you need to make classes, separate them so that you can make some decisions. To give an example, supervised learning would be somewhere like you enter a room full of people and you identify this person is Indian, this person is Chinese. This sounds racist. So, but yeah, so this person is Indian, this person is Chinese, this person is probably from the UK. But uh, you are given this data that this person is Indian, this person is Chinese, and by looking at 2 3 Indian people, you get to learn how Indian peoples look, and then further, if I give you some random person, you'll be able to take a decision and say, this person might be Indian, this person might be Chinese. But in unsupervised learning, you cannot. I mean, in that room full of people, you just see all people and you are not given any information about this person might be Indian, this person might be Chinese. Since you are not given any information, you need to predict on yourself based on some features which you can probably see and cluster them together. So clustering, as the name suggests, is a group of algorithms which is under the unsupervised learning domain. Uh, Along with that, we have some more algorithms like dimensionality reduction. We'll discuss about them later on. And reinforcement learning is the learning in which uh, you learn through trial and error, such that you take a good decision, you get some rewards, and on getting those rewards, you try to make better decisions so that you can accumulate more and more rewards. And if you perform some wrong actions, your there will be negative points, just like some competitive exams, and you try to avoid those errors. And this is how the model actually learns through trial and error. All right. So, okay. So some famous algorithms are regression and classification. Now, this regression and classification thing, uh, these two algorithms belong to the supervised learning domain. Uh, Let me tell you about what regression and classification is. Uh, Regression would be, um, the data for regression is the output column will be numerical. All right. So this is the most basic definition of a regression setting, that the output column would be numerical. It's generally continuous data. Probably the output column might be your salary, and the input column in your data might be might be how much your CGPA was in the college. So if you have a CGPA of 5, your salary might be 20,000. I don't know. And Yeah, so this is a regression setting in which the output column is numerical and is continuous, whereas classifications are those algorithms in which the output column have some classes or are discrete. And what do you mean by discrete? That is, the output column might be if you were placed or if you were unplaced. Depending upon CGPA data, the output column might be you have a CGPA of 5, you were not placed. So the output might be 0. If you have a CGPA of 6, you might be placed, so the output might be 1. And yeah, so the output column just has zeros and ones. So this is classification setting in which we have classes in the output column. So I guess I'm clear about regression and classification. If anyone has some question, they can ask. And let me move to clustering. So clustering and advanced algorithms. Clustering comes under the unsupervised learning domain, and clustering, as the name suggests, clusters the input. Since in unsupervised learning we don't have specific outputs or labeled data, we just have unlabeled data. That is, you are just given the input vector, probably x, and you need to cluster them together based on some observed characteristics. So clustering comes under unsupervised domain, and by advanced, here it's neural networks, but sorry, by advanced, we meant neural networks here, which comes under deep learning, and deep learning forms the basic of neural networks. Sorry, neural networks forms the basic of deep learning. All right. So linear models and regression. So in our session, we'll be learning about linear models and specifically linear models used for regression settings. As since I probably am clear about regression, I just explained regression, and I think we can jump on to the problem. So, all right. So regression. Now, regression is a problem in which the output data is numerical and is continuous. And for regression, we generally have two types of regression. I mean, two types of algorithms. The first one is the simple linear regression algorithm, and the other one is multiple linear regression algorithm. Now, you might be thinking there are some other regression algorithms as well. Probably you have heard names like polynomial linear regression or logistic regression. Yes, they are regression as well. But as of now, we'll be discussing about simple linear and multiple linear since these two are related. And we'll be discussing about SLR and MLR. So the first one is simple linear regression. So simple linear regression is, first of all, it's an algorithm. The difference between simple and multiple linear regressions is that in simple linear regression, you are given just single input column and a single output column. Now the output column is always going to be single, so there's no difference in that, but the input column is just going to be one column. This is simple linear regression. As we can see written in the PPT, a statistical method, simple linear regression is a statistical method that allows us to summarize and study relationships between two continuous variables, right? Two continuous variables. One is going to be the input variable and the other one is going to be the output variable. The first one, which is x regarded as x, this is the independent variable, which is your input. And the other one, which is denoted as y, this is the dependent variable and your output. Now, as we can see from the definition, y should be continuous. That is, the range of y should be from, let's say, minus infinity to plus infinity. And there would be continuous data, no discrete data. Since this is a regression setting, so, all right, if a neural network does not use any activation function, can it solve complex problems like image classification? No, it cannot. I mean, neural network, for providing an output, you always need a activation function because the base of neural network is a perceptron, and perceptron always work with activation function, or else you cannot work. Yeah. Okay. Amira. Sorry, I cannot pronounce your name. Your name seems a bit large. Okay, so yeah, so simple linear regression, y equals mx plus c. Now, what is this y equals mx plus c? We'll be learning more about y equals mx plus c when we'll be moving on to our notepad. Okay, so I feel like this is the best time to move on to our notepad. Can I get the notepad on the screen, please? There is some latency. All right. So we are going to learn about simple linear regression. The thing is, my handwriting is very poor, so please don't curse me. Just a second. Yeah, so the input data would be x and y. Now let us assume the x values are probably 2. For 2 we have 4. For 3 we have 12. For 4 we have 14, and like this. Now you are said at some point the x value becomes 20 and you need to predict what the y value will be. Now how can you do so? The first thing you can make is a graph so that you can visualize the relationship between x and y. As you can see, there is a linear relationship between x and y. Let me see. If I can increase the size, probably this one is okay. Oh, sorry. Consider this is your data. Now, I've not written what x and y is here, but you can assume x to be an independent variable and y to be some dependent variable which depends on x. So x and y could be anything. I'm not giving some proper names to it. So we can see x and y is linearly related. That is, the correlation, if you find the correlation, which is gamma, is going to be 1. I guess you all are familiar with correlation. So the correlation between them is 1, that is, they are linearly related. So the first thing I can do is create a model, because in machine learning, all we do is create models. So, all right. So what is a model all about? A model can be thought of as a box which takes input x and provides output y. But why here? Sorry. But why here was our output column, right? So this y should be different because this is the predicted y. So we call the predicted y, we denote the predicted y to be y hat. All right. We call the predicted y to be y hat. And so what does this y hat do? This y hat predicts the value for a given x. Consider a given x is 20, just like I said. So what would be the predicted output? That is what our model does. It predicts the output given the input. So for a basic model, for a basic model, what we can do is we can say the output y hat could be the mean of the of all the observations in the y column. But this would be very basic, right? Let the mean be 12. So for any input, if user provides any input, I'm always going to reply with the mean. This is going to be a very basic stuff, and any human uh, will be able to do this. So what is special about your model? So the special thing about our model is going to be uh, our model. Our model has a lot of intelligence. That is, our model can see that this data has a linear relationship. So why not draw a straight line on it? Why is this not working? What is happening? let's draw a line. And this line, let this be our model. Because we can see the data is linear. So we can create a line which can predict the outputs. Now, how can this line predict the output? Consider you have this data, which is this point. Now, this point on your data set has this output, let me call it y1. But this point, according to our model, has this output, let me call it y1 hat, right? So for this data 1, y1 was the actual output which was present in our data, and y1 hat is the output our model predicts. So we can see y1 and y1 hat are two different quantities. So there is some error which our model is making because we cannot make a perfect model at this point. So what is this error? How can we describe this error? Now we describe this error to be the difference between y1 and y1 hat. Right. So we say the error at this point. Man, this is so boring. All right, this is working. So we can say the error our model is making is y minus y hat. Now y1 minus y1 hat, but this was the error made by the model for a single data point. But we can see there will be a lot of data points and the model will be making some error on all of them. So let's modify this into summation. Let's add up all the errors, right? So we get y minus y cap summation, and let's take the mean of all of them. So let's divide it with the number of observations in our data. But as you can see, since the line is here, there will be some points above the line, there will be some points below the line. If you are considering this distance is a positive distance because y1 is greater than y1 hat. But for this point, which lies below the line, this distance is negative because y1 is actually lesser than y1 hat. So if we add up like this, we might end up getting zero error, which will not be a right thing because the error is not zero. So let's square this term. All right. If we square this term, the good thing would be we are squaring the errors. So the negative will become positive as well. And then we are taking the mean of the squared. Right. So this is going to be our error, and we will be calling this MSE. I guess you all will be able to identify what this MSE is. This is mean squared error. Right. So this is going to be our error. Now, our model makes this error on the given data. But first of all, our model is just a straight line, right? So the output value, which is going to be y cap, is going to look like the equation of a line. So the equation of a straight line is mx plus c, but here in machine learning context, we'll write it to be b. B is a good choice. Okay, so this is going to be our model. So this is going to be our model. And what is m here? The term m represents the coefficient of x here. We call it, you can call it to be the weight. In machine learning context, we call it weight. But according to a line, you can call it to be the slope as well. And B, in machine learning concept, it is called bias. But according to the line, you can call it to be intercept. Right. So weight, slope, bias, and intercept. So for creating this model, we need to identify the values of m and b because we know what is x. And if we know x, along with that, if we know m and b, we can write the equation of the line. The equation of the line might look like 2x plus 3. So m can take a value of 2, b can take a value of 3. But we need to find appropriate values of m and b because our line can be this, our line can be this as well. But since the data was spread like this, a line like this would not be, properly showing the correlation of x and y at this point. But this line would be better. So we use this concept of error, and okay, so the error, let me denote it with e. So the error is a function of m and b, because what was the error? The error was 1 upon n summation of y minus y cap squared. Now y cap has this value mx plus b. So let me just substitute this value. So we have 1 upon n summation of y minus y cap is mx plus b is going to be minus b squared. And this is going to be our error. All right. So as we can see, our model should be such that, first of all, this error function, if I draw this error with m, it will be somewhere like this, because at some value of m, you'll be getting the lowest error possible, and for b as well, you'll be getting something like this again. So for some value of b, you'll be getting the lowest error. So we need to identify for what value of m and b we'll be getting the least error, right? So, so the first thing we can do is we can just differentiate e with respect to m, and we can just call it to be 0 in order to get the minima. And for this case, we can differentiate e with respect to b, and we can call it to be 0 again for getting the minima for these e versus b curve. Right, let's add a page. Yeah, this is okay. So the first thing we are going to do is we are going to find del of e by del of b. Now this is going to be 0. What is del of e? So we are going to find del b, del b of the function was y minus, sorry, it was summation 1 upon n summation of y minus mx minus b squared, right? And this is going to be 0. So you can see, uh, if we find the derivative, so this 2 will come out, right? So we have 2 upon n summation of y minus mx minus b, and for b we'll have a minus 1, so this minus 2, and this is going to be 0. Now let's send this 2 to the right side. So we are left with minus 2 to the right side. Okay, so we're left with summation of y upon n minus m times summation of x upon n minus of summation of b upon n, and this is going to be 0. Right. So what is this summation of b upon summation of y upon n? This is basically the mean of y, right? So this is the mean of y minus we have m times the mean of x here minus of, now summation of b is just a constant, right? This is the bias term or the intercept. So this is going to be a constant value. So we are adding the bias. The summation goes from 1 to n because we have n distinct data points or the observations or samples. So this is n times b. Summation of b n times would be n times b divided by n. So this is nb upon n. So n will cancel out. And on the right hand we have 0. So from here we get a value of b. Now b comes out to be y bar minus m x bar. Right? Can I highlight this with something? Let me see. No, I cannot. Sorry. Right. So this is the value of b we got. Now for our next step, we need to find del e upon del of m. So we need to differentiate the error function with respect to the slope. So, and we need to equate it with 0 to find the minimum. Now, the del of e at this point would be del of del m, and we have 1 upon n summation of y minus mx minus of b. Now b, we are provided a new value of b at this point. So we'll be substituting this value. So minus of b would become minus of y bar and minus minus plus of mx bar. So we have this thing, and this is going to be 0. Right, so we have 1 upon n. Okay, so we are going to differentiate this term. So the 2 will come out, and this is going to be 2 upon n. We are left with summation of y minus mx. Okay, now along with this, uh, since we are differentiating with respect to m, so we have minus x for this first term, we have minus x, and for this second term, we have plus of x bar, right? So So let me just keep this one as it is, plus of mx bar, and we along with that we have um, minus of x plus of x bar, and this is 0, right? Yeah. So what we can do is we can send this 2 to the right hand side again, and we can take minus common from here and send it to the right hand side. And if we do that, we get summation of, okay, just a second. So what did I say? Yeah. So we can send 2 to the right hand side and we can take minus common. So this is going to be, okay. So from this y and from this y bar, we can put them together. So we can say this is y minus of y bar. And for this mx and mx bar, we can just take m common. Okay, so we can take m common and we can say plus of m, uh, plus of m times x bar minus of x. Right, and this thing is going to be inside a bracket, and the outer one would become, since we have taken minus common, so this is x bar minus x as well, and this is 0 as usual. Okay, so now this x bar minus x will be putting it inside these square braces, and so this will be multiplying with all of them. So this is, okay, so this is summation of y minus y bar times x minus x bar. Sorry, this is going to be, oh, no, 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 sorry, sorry. I wrote something wrong. So this is going to be x minus x bar. So this is x minus x bar, and plus of m times we have x minus x bar squared. There is something wrong here as well. Let me rub it. If I take m common, I get x minus x bar here as well. Sorry, fell a bit behind, but for the error, why can't we take a mod instead of going for the square method? All right, if we take the mod, mod is first of all not differentiable. We can take the mod, but the thing is, this is the way I'm solving this error function or differentiating it. This is known as the ordinary least square methods. If you use scikit-learn uses this ordinary least square method in its original class, where it has implemented simple linear regression. But the thing is, we are going to use some other optimization techniques in the future, which is known as gradient descent. This is a very famous optimization technique. You guys can refer to some good channels. So gradient descent actually uses mean squared error. But as well as here, if you take ordinary least square, since we are differentiating, we cannot differentiate a function which has modulus, because modulus is non-differentiable, as you all know. So we cannot differentiate it. Moreover, for the gradient descent method, mean absolute error, which you are talking about, will be again non-differentiable. So for both ordinary least square and gradient descent, which are the most popularly used optimization techniques, we don't use mean absolute error because we cannot differentiate it. All right, will it be available for recording? Not getting. Okay, so if we take m common, so this is going to be x minus of x bar. So this is x minus x bar squared, all right, equals 0. So we can just divide the summation to both of the sides. Okay, let's take another sheet, add a page. All right, so we can divide the summation to the left hand side as well as the right hand side. So we get, what was here? uh, y minus y bar times x minus x bar. Okay, so we can take the m and differentiate it. Sorry, uh, just a second. Okay, so I made some mistake over here as well. We need to take minus m common. All right, we need to take minus m common in order to get x minus of x bar. So we can divide this summation to this term and to this term as well. Okay. Uh, okay. So we get summation of x. Oh shit! This thing is happening again and again. I don't know what is this. Okay. X minus of x bar times y minus of y bar, and we have minus of m times summation of x minus x bar squared, and this thing is equating to 0. So we can say, since we are trying to find the value of m, which is the least value of m, this is going to be summation of x minus x bar times y minus y bar upon summation of x minus x bar squared. So this is x, okay. Oh, yep, this is x. So this is going to be our value of m. So we got the value of m, which is the least value of m, to be x minus x bar y minus summation of x minus x bar times y minus y bar upon summation of x minus x bar squared. Okay, and we got the value of b as well somewhere here. Yeah, the b value was y bar minus x bar. Now, can I get the PPT? Can I get the PPT? Okay, yep. So, so I guess you all can now relate to what y equals mx plus c is. This is basically the line we just created, which is basically the model we are talking about. And c is what we have referred to as b over in our notepad. And we have just found out the ideal values of m and c for minimizing the error. Okay. So this was the example we had. I should have said this earlier. Okay, so this example is a basic real life example. The diameter is 6, 8, 10, 12, 14. This is the diameter of pizzas and the price on the output column. So the price is the y we are talking about, and the diameter is the x we are talking about. So for x, we have corresponding y. So you are given x values of 6, 8, 10, 12, 14, and y values of 7, 9, 13, 17, 18. Now, somewhere if you are said to find the y value for a 20-inch pizza, uh, you'll be able to identify the value based on the line we created, because you know the output value would be y cap, and the value of y cap is mx plus b. We have the values of m, we have the values of b as well. Now we'll be implementing this. Don't worry if you're not getting about how we can calculate the values of b and m depending on this data set. We'll be implementing it shortly. Okay, let's see the next slide. So the next slide is, how do we find the best fit? So here, as you can see in the slide, we need to minimize the error between the actual values and the predicted values. So as we said, if this is the line, this is the real point. The real value of this point lies on the y-axis, which we are calling it to be y1. Let this point be 1. So this y value is y1. And according to our model, this point should lie here. So this value would be y1 cap. Okay, so this is this y1 and y1 cap. Here it is referred to as yi and yi cap, because there will be not only one data point, there will be many data points. Let the data points, number of data points be n. So we are finding the error to be 1 upon n, which is meaning all the errors. Summation of yi minus yi cap, that is we are doing the summation of all the errors over all the data, and we are squaring them up. Somebody just asked, why are we not taking modulus? We are not taking modulus because we cannot differentiate a modulus function, because it is not differentiable. It is not continuous. I mean, it's continuous, but it breaks. So we are not able to differentiate that. But yeah, if you can take it, if you find some other algorithms which can do so, um, that error is actually termed as MAE, that is mean absolute error. Okay. But here the error is being referred to as the cost function. Now I have referred to as an error function. This is cost function, and somewhere again you'll be hearing two other terms, which is a loss function, and the other one is uh, objective function. Okay, so there are four terms. If you guys know the difference, uh, it's okay. If you guys don't know, you can say it to me in the chat, and I'll be explaining it. Okay. So, but yeah, kind of all the things are same. If someone wants to know, I'll be explaining. So let's keep this as a suspense. Okay, so the mean squared error, this error is termed as MSE. This is the mean squared error. We are taking the mean and the square of all the errors. So we are finding the error yi minus yi cap, squaring it up, and then taking the mean. Okay, so our goal is to minimize the MSE to find the optimal MSE. Now, how are we minimizing this mean squared error? We are minimizing this by finding the gradient, not the gradient actually, we are minimizing it by finding the uh, different partial differentiation of this function. Since this is a function which depends upon two variables, we are partially differentiating it with respect to m and with respect to b, and we are equating it with 0 in order to get the um, mean, I mean the least values. But the thing is, if we differentiate it with 0 and if we differentiate it with respect to m and b and equate it to 0, nobody asked me why that thing is, always finding me the minima, because we can also find the maxima as well. But nobody asked me why is this not the maxima, this is just the minima. Because for minima, again, we find that the double derivative, second order derivative, would be greater than 0, but nobody asked me that. All right, I guess you guys know. um, okay, let's move. Okay, this is multiple linear regression, but before that, let's move to a hands-on programming for this simple linear thing. Okay, so can I get my Colab notebook on the screen? If the MSE value is 0, what does that imply about regression line and the data points? Amir Rahim Ansari. Okay, if the MSE value is 0, okay, if the mean squared error is 0, if the mean squared error is 0, now this can become 0 if the summation is 0. And since we are taking the square, all of the values will be positive, right? So summation of positive values can only be 0 if you have all the values to be 0. And for all the values to be 0, yi should be equals to yi hat, right? If yi is equals to yi hat, you have created the best model line. So the mean squared error, if it's 0, you have created the best model. I mean, it should not be 0, it cannot be 0 actually. Perfectly fitted model. Yes, but since we have discrete data points, we cannot make it perfectly fitted unless and until we use some polynomial features in our model. Since this is a linear model, we cannot do so. Overfitting. Okay, yeah, overfitting. Overfitting. You guys know a lot. Yeah, this is actually overfitting. Okay, let's move on to the linear regression using Python. So we have just imported some libraries. I guess all of you might be familiar with pandas and numpy, and we have used matplotlib to plot the data. So we have generated some synthetic data using the make regression class from scikit-learn. Um, so we have taken 200 samples. So the n value will be 200. The features, there is going to be one input feature, and the target is going to be 1, and the noise is 30. Let's skip noise as of now. Okay, let me reconnect. Okay, so let me just run this cell once again. This is connecting. Why is it taking too much time? Yeah. So okay, this is running. This is running. Okay, let's create the data. The data is being created, and we are going to store it in X and Y. Okay, so X and Y are numpy arrays at this point. So we are converting it to pandas data frame in the next cell. So yeah, this is our input feature. We can just call it to be X and the target to be Y. So this is our X and this is our Y. Okay. So this, as you can see, there is a single input column and a single output column. So this is a perfectly simple linear regression model. I mean, we are going to use a simple linear regression model. But yeah, before that, we need to see the plot of x and y in order to identify the correlation. Okay, the dimension of x is, as you can see, 200 cross 1. We have 200 values, and dimension of y is 200. Yeah. So as we can see, this data is having a linear relationship. If you find the correlation is nearly going to be 1. I mean, the Pearson correlation coefficient. Okay, so we are importing sklearn model selection for doing the test train test plate, but we have not used train test plate in this simple linear regression. I mean, yeah, we'll be using train test plate um, after a few minutes. But as of now, you're not using train test split, so we are taking the whole data. I'll be explaining train test split when we'll be moving on to the next code. Okay, so here we have used the whole data. We have created an object LR of the linear regression class from sklearn, and this fit attribute is basically fitting that model and calculating all the intercept and the slope values. And then y hat, we are predicting the y hat. Y hat is again going to be looking like a column vector. By using lr.predict, we can take y hat, and yeah, we can print the intercept, we can print the slope by calling lr.intercept and lr.coefficient. So if we can run, yeah, we are getting the intercept value to be 2.808 and the slope value to be 95.6077. Okay, so intercept and slope. This is the value of intercept and slope using scikit-learn's um, linear regression class, but we are going to do something different. Okay, so this is the linear regression line which we have created. So this is basically our y cap line, which is mx plus b. And as you can see, this looks perfectly fine. Okay, now here comes the most interesting part. We are implementing our custom linear regression. Okay, sorry. So let me just run this. Import numpy as np, and then we are implementing our class. Now let me describe the code. The class is named mySLR, my simple linear regression. Inside the constructor, we have just initiated two two values, the intercept value and the coefficient value, right? Um, so these are the instance variables, right? So we have two methods. First of all, the fit attribute and the predict attribute, two methods. The fit method is going to take x and the y inputs and the outputs. So first of all, we are converting x to an NP array, y to an NP array, even though it was an NP array. Okay, but never mind. We are then calculating x of mean of x and mean of y. Why are we doing so? Because as we can see, for finding the value of b, the b value was y bar minus of m x bar. So we need to calculate y bar, which is the mean of y and mean of x as well. Okay, so we have np.mean method to find the mean. Then for finding the value of m, which was summation of xi minus x bar times yi minus y bar divided by summation of xi minus x bar squared. So this is summation. Okay, the summation term is very important here. Summation means we need to find xi minus x bar times yi minus y bar for all the i's. So we create a loop in the range of x dot shape 0, that is for the number of rows, because the summation will run up to n, which is our input dimension, number of rows. Here it's 200. So numerator, so every time we are getting inside the loop, we are taking a row and we are multiplying xi minus x bar, that is x of I minus x of mean, which is x bar, times yi minus y bar, and we are adding it to the numerator variable. The numerator variable is initialized with 0, and then we are adding it up for all the values of I, that is for all the rows, and then we are calculating the denominator in the same way, which is xi minus x bar squared, and we are adding it up. So after getting out of this loop, we have calculated the numerator and denominator. So our um, uh, coefficient term is going to be the numerator divided by the denominator, and the intercept term is going to be y mean, that is y bar minus of m, which is self dot coefficient, times x bar. Okay, and we have another method, which is the introduce yourself. Uh, okay, I'll be introducing myself. Okay, okay. Let's not move out from the topic at this point. I'll be introducing myself again. Okay, even though I did so. Okay, so def predict, which is the predict attribute, which is going to predict the output or the y hat for all the given input. So we take the x here, which is the input, and we convert it to a numpy array by calling np.array, and then we are going to return the output. Now the output is y hat. What was y hat? Y hat was mx plus b, the simple line, right? So m self dot coefficient times x plus b, which is self dot intercept. So we have implemented this class, and then we are creating an object of linear regression. That will be my SLR. It's called my SLR, right? No, SLR was small. Okay, so my SLR. Now, as we can see, we just got the intercept value of 2.808 and the slope value of 95.607. Now, comparing our model and the model which was there in scikit-learn, we can see our model's intercept and the original intercept are the same, because as we said, I mean, it's same up to a lot of decimal points. Okay, as we said, as I said, internally scikit-learn uses the ordinary least square methods for finding the intercept and the slope. So we just got the same values. So that's a success for us. And we can plot our line. This green line is our line, which is just the same. I mean, we have plotted red and green, both of the lines, but as you can see, the green comes after red and both have overlap. So we cannot see the red line here. Okay, multiple linear regression. Okay, can I get the PPT again? Can I get the PPT? Okay, all right. So multiple linear regression. Now we'll be moving on to multiple linear regression. I guess the this is a random this is random video I'm seeing. Teaching very nice, better than my online course in college. Thanks, man. Thank you so much. Okay, so for the multiple linear regression, we are moving on to multiple linear regression. Now, what is multiple linear regression? What is the difference between simple linear regression and multiple linear regression? I guess I have time to describe multiple. Okay, 6:56. We are moving pretty fast. Okay, so multiple linear regression. Now, the difference between simple linear regression and multiple linear regression is that, as the name suggests, this has multiple input features. The multiple terms is a term used for input features. So, in simple linear regression, we had a single input, single x value, but for multiple linear regression, we'll be having multiple x values, because real life data is not that simple. It does not have, just one x value and just one y column. So we have a lot of other x and y's as well. So multiple linear regression has a lot of x values and a single y. I mean, not lot of x values, lot many columns. Okay, so let me introduce you to some basic machine learning literature terms used for these. The columns are said to be feature, and the output is said to be label. Okay, the output is said to be output as well. I mean, there's no harm in saying output to be output. The input columns are known as the features. Okay, so for multiple linear regression, we have multiple features, whereas for simple linear regression, we had just one feature. Okay, this is the basic difference. But the thing is, this is linear regression, so we are just going to create a linear model. And for creating a linear model, we just draw a line. I mean, for two-dimensional data, which was in simple linear regression for x and y, we created a line. But here there will be many x, I mean, a lot many features. So this is not going to be two-dimensional anymore. This is going to be multi-dimensional. I mean, more than two. It can be three, it can be four, it can be anything. So in these cases, we cannot draw a graph. I mean, this graph shown here is a three-dimensional graph. So this is the y attribute, which is there in uh, the perpendicular axis, and the x1 and x2 are there in the horizontal axis. So Uh, as you can see, this this thing which is drawn, and this is not a line. This is actually called a hyperplane. A hyperplane is kind of a line. I mean, this is a plane actually, but you can think it to be a line. But this is in hyperdimensions, that is multidimensional uh, data. For multidimensional data, we don't draw a line, we just draw a hyperplane. So this line is basically the same thing as hyperplane. Um, I mean, hyperplane is just a line in multidimensional space. Okay. So the equation of line was mx plus b. So we just had one input x, and we had m with it. I mean, which was the slope, which is also known as the weight. So the weight of x, coefficient of x multiplied by x plus a bias term, which is a intercept. But here there will be many x. So there will be many x, x1, x2, x3, and every x will have their own coefficients. Right. So we can write the line equation, I mean the hyperplane equation to be y cat, which is uh, you can say m1 x1, m2 x2, m3 x3. Okay. And finally one intercept term. But this thing is written in a modern way here. uh, this is actually the way in which we write equations in machine learning. So the b naught here, b0 here, y equals to b0, as you can see. This is the intercept term, okay, or the bias term. So let's keep it separate. And we have b1, b2, b3, b4, and a lot of b's till bn. These b's are the coefficient of all the input x's, x1, x2, x3, and these b's are actually the weights. Okay, so for finding the equation of this hyperplane, we just need to find these b values. Okay, along with this b values from 1 to n, we have another value which is b0, which is actually the bias term or the intercept term. Okay, so in the last simple linear case, we just found out the value of m and b, but for this case, we'll be finding out the value of b0 and a lot of other b's. If anyone has some question, you can ask. Let me drink some water. I guess 15 people are watching. Guys, you can at least share it with your friends and all. I mean, I don't think so. I'm teaching that bad. This will be available again in the future. Oh no, 13 people are watching. Oh, that's a very poor number. Right, I'm not getting any questions, so I'll be moving forward. So, what is there in the next slide? Okay, the mean squared error function used here will be the same thing. Let me not get into that early. So, can I get my notepad, please? Can I get my notepad? All right. So we are moving on to multiple. Sorry. Oh, my handwriting is too bad. We are moving on to multiple linear regression. All right. So for multiple linear regression, we have a lot of x values. Let this be x1, let this be x2, let this be x3, till we have probably, what should I take? Let it be n. Okay, let it be n. Let it be m. So we have xm and one y value. Right. So now we are not writing any data. We are just writing if the regression model predicts well on training data but poorly on the new data, what logical issue is the model suffering from? If the regression model predicts well on training data and poorly on new data, okay, so your model um, has bias. Okay, okay. I mean, what errors will we encounter in that situation, the accuracy of the model will drop. Uh, for that, I need to introduce two concepts, which is the bias and the variance in the model. Um, okay, we'll be describing bias and variance shortly. I'll be describing. Okay, right. So x1, x2, x2, x3 till xm, and we have y as well. Hmm. The first one x1. Okay, let it be x11. The next one let it be x12. The next one let it be x13, until the last one will be xm, sorry, x1m, and let this be y1. The next value will be, the second row will be x21, x22, x23, and we'll have till x2m and y2. Like this, we will have, okay, there will be, okay, let it be n. So let this be m, let this be n. Hmm. Okay, let this be n, and let this be n. So this is x in 1, x in 2, x in 3. We have x in m, and the y value will be y of n. Right. So this is our data set. Okay. Now, so what we are doing is we are predicting this y values, right? We are predicting all these y values, but here there are many y values. So let's represent it in a matrix form. So we are predicting y1 cap, y2 cap, and like that we are predicting till yn cap. So we are actually predicting this vector. Now y1 cap can be written as, let me not write it b, let me write it beta, because beta is actually used. So this is beta naught plus beta 1 x11 plus beta 2 x12. We continue it till beta. Okay, so we'll have beta 1, beta 2, beta 3 till we have how many betas? Let me calculate. Mm, so for m, we'll have m plus 1 beta. So this is beta of m plus 1, beta of m plus 1 times x 1m. The next one would be beta naught plus beta 1 x 21 plus beta 2 x 22 till beta m plus 1. Oh, sorry, not m plus 1, man. This is going to be beta m. I was wrong. Sorry. This is going to be beta m uh, minus. No, this is going to be plus. We have beta m x 2m. Right. And like this, we'll have beta naught plus beta 1 x in 1 plus beta 2 x in 2, and we'll have beta m x m, sorry, x in m. Right. Okay. So this matrix, we can call it to be a y cap matrix, which is y1 cap, y2 cap, y3 cap, continuing till yn cap, and the right hand side matrix. Okay, we'll be decomposing this right hand side matrix uh, into a linear combination. So let me write. So what can we write? We can write y cap to be equal to. Okay, if I write the first line to be 1, x11, x12 till uh, x of 1m. Okay. 1 again here, x21 plus x22 plus x2m, and we have 1 x, this was n1, x n2, x in m, and this is going to be um let me say beta, okay, beta naught, beta 1, and we are going to continue till uh, beta m. Okay, so can we write the right hand side matrix to be like this? I guess we can. Okay, if the regression model predicts well on training data, okay, I just said that. Okay, so beta naught, beta 1, until beta m. Now you can see if we multiply this matrix, beta 1 will get multiplied with 1, beta, sorry, beta naught will get multiplied with 1, beta 1 will get multiplied with x11, and we'll be finally getting the same matrix, right? So there's no harm in writing it like this. Okay, so we can probably open this matrix up. I mean, uh, let's not open it. Uh, let's write this whole matrix to be the X matrix, and let's write this matrix to be the capital beta matrix. So our equation will be y equals x beta, where x is this matrix, 1, x11, x12, 1, x21, x22, and the beta matrix is the column vector of beta naught, beta 1 till beta n. Okay, let me write the dimensions as well. What is the dimension of y? Y goes from y1, y2, y3 till n. So this is number of rows is n, number of column is 1. Okay, now what is the dimension of this X matrix? The X matrix has n columns and m plus 1, sorry, n rows and m plus 1 columns. So this is n cross m plus 1. And what is the dimension of this beta matrix? The beta matrix has m plus 1 number of rows and n columns. Right, so we can multiply this. We can just verify the dimension. We can multiply this. The result will be n cross n. Sorry, yeah, the result will be n cross n. Actually, this is a summation term, so this will lead you to be 1. Okay, so this will lead you to be 1 result. So one row has just one value. So you can probably, uh, you know, write this n to be n cross 1. Okay, no, sorry. I did something wrong, man. This is 1. Nobody said me. Okay, so n plus 1, n cross n plus 1, n plus 1 cross 1. So we get n cross 1, and this is the same dimension as your y. So we just verify the dimensions as well. Okay, let me delete this thing. Right, we'll delete this as well. And let's add a new page. Okay, so here, now what is the error? The error for the first value is y1 minus y1 cap, right? The error for the first value is y1 minus y1 cap. The error for the second value is y2 minus y2 cap. I mean the absolute error, which is known as the residual as well. And we have y, I guess n minus yn cap. This is the error, right? Let me call this to be e. But our mean squared error was actually summation of yi minus yi hat squared. So how can we get the square term? If you observe carefully, we can just multiply this thing. Okay, let me keep it. We can just multiply this thing. That is, we can create E transpose E. Okay, just a second. Let me say the mean squared error is capital E. Now this can be created by E transpose E. Verify. What is E transpose E? This is y1 minus y1 hat, y2 minus y2 hat, and we have yn minus yn hat, right? And E transpose, okay, so E transpose, we are transposing it and again multiplying it with itself. That is y1 minus y1 hat, yn minus yn hat. Okay, so if we transpose it, what is the dimension of this? The dimension is n cross 1, and we are transposing it, right? So this is going to be 1 cross n. This is going to be 1 cross n. And what is this thing? This thing is n cross 1, right? And we are going to multiply this. So we are going to get 1 cross 1, which is going to be the summation of all these. So, so the error can be written as E transpose E, provided you understand what E is. And E is this column vector containing all the residuals. So, all right. So we are just going to work with E here, just like we worked with E on a simple linear regression case, which was 1 upon n summation of yi minus yi cap. So what E is? E is E transpose E, which is small e. Now what is E? E is y minus y hat. Right. This was our E y minus y hat, this vector. Now see, y minus y hat. Y is this column vector containing all the real values. Y hat is the column vector containing all the predicted values. So we get y minus y hat. We are transposing it and then multiplying with y minus y hat again. Right. So just like we said, the value of y hat is x beta. We just said it here, right? The value of y hat was x beta, right? This was the value of y hat. Let's use the value of y hat. So this is going to be y minus x beta transpose times y minus x beta. Hey, so y minus x beta transpose. So since we have transpose, we are going to distribute transpose to y transpose and then minus of x beta transpose, and we are going to multiply it with y minus x beta. Right. So this is going to be multiplying all the terms y transpose y minus of x beta transpose y, right? Minus of y transpose x beta minus of x beta transpose x beta, right? Now observe one thing very carefully. This term which we have and this term, these are equal. So we need to prove it. How are they equal? Let me say, what is the dimension of x beta transpose? X had a dimension of, what is the dimension of x? The dimension of x is, let me see, the dimension of this x was n cross n plus 1, right? So this is n, man, such a drag, n cross n plus 1. Okay, so you are transposing it. So x, all right, let's not say we are transposing it. Let me say, what was the dimension of b? B was running from 0 till m. So we have 0 times m plus 1, I guess. Yep, 0, sorry, number of rows was m plus 1 cross 1, right? So if you multiply them, what do you get? You get n cross 1. So x beta has a dimension of n cross 1, right? Let me say, so x beta has a dimension of n cross 1. Now y, what is y? Y has a dimension of, y goes from 1 till, I guess we took it to be n. Yep, it was n. So y goes from 1 to n. So this is n cross Oh man, y has a dimension of n cross 1, right? So we are multiplying uh, x beta transpose. Did we go wrong somewhere? X beta transpose times y, x beta transpose. X beta was n cross 1. Okay, so we are taking x beta transpose. So this is going to be 1 cross n, right? It's going to be 1 cross n. If this is 1 cross n and we are multiplying x beta transpose with y, so we get 1 cross n times n cross 1, right? So we finally get x beta transpose y is actually 1 cross 1. So this is just a single scalar value. Similarly, if you try to find out y transpose x beta, what is y transpose? Y transpose is going to be 1 cross n. We're multiplying 1 cross n with x beta. X beta is n cross 1. And 1 cross n times n cross 1. So this is again 1 cross 1. Right. So since these are equal, I mean these are scalar terms, can we say x beta transpose y? And if you transpose it whole together, what are you getting? This transpose first goes to y transpose. So this is y transpose x beta transpose transpose, and that is y transpose x beta. So you are just transposing this term. I mean, you are just transposing this term and you get this term again. Since this is a 1 cross 1 term, you are transposing it and you are getting the same thing. That means that x beta transpose y and y transpose x beta are the same thing. I mean, they are the same values, right? So I just explained why are the same. I guess I guess this is clear to all. So these two are the same thing. So we can write these two to be, let's say we take x beta transpose y. So we take minus of 2 times x beta transpose y. So in our new page, we'll have the value error is going to be y transpose. This is y transpose minus of uh, 2 times x beta transpose y. 2 times, oh sorry, 2 times x beta transpose y, and we have the last term was x beta transpose x beta. Now this was minus or plus? This was, I guess this should be plus, man. Made some mistakes. Minus of x beta transpose, yeah, this should be plus. So this is plus of x beta transpose x beta. Now let me open it up a bit. So this is y transpose minus of twice of um, if you take transpose of x beta, this is going to be beta transpose x y. Let me do something wrong. Get um, okay, y transpose x beta. Okay, let's see if we get something wrong. Let's see plus of x beta transpose x beta. So this is going to be beta transpose uh, x transpose x times beta. Is it x beta transpose y or is it y times x beta transpose? Y transpose y and minus of x beta transpose y transpose x beta, y transpose x beta. Can I take y transpose x beta? Let me see. If I face some problem, I'll be taking the other term. So, I mean, I should take the other term, man. Just a second, guys. Uh, y transpose x beta, if I take y transpose, this is going to be x transpose. Sorry. Let me take this term. Okay. Let me take this term. This term. Let me take this term. This will be easier. So this term was uh, twice of y transpose x beta minus of twice of sorry twice of y transpose x beta twice of y transpose x beta, right? Y transpose x beta. All right, fine. So we have error to be y transpose, sorry, this was y transpose y, man. Y transpose y minus 2y transpose x beta plus of beta transpose x beta. Now we can see error function is a function of beta, just beta. Okay, so we can derive, I mean, we can differentiate error with respect to the beta value and obtain the minimum value of beta for which, I mean, not the minimum value, the optimal value of beta for which our error would be the minimum. And for that, what can we do? For that, let's differentiate error with respect to beta. So this is not going to be a partial differentiation. This is going to be a direct differentiation. Sorry, dE upon d beta, and we are going to equate it with 0. Right, let's start. Now this is going to be a matrix differentiation, so I don't think so you guys are familiar with matrix differentiation, but as of now we'll need a single formula, and I'll be explaining you the formula. Okay, I mean, um, you can go and refer to matrix differentiation in the future, but as of now there's going to be just one formula. We'll be explaining that. Okay, so del E upon del B equals 0. So we have y transpose y minus of 2y transpose x beta plus of beta transpose x beta. Okay, so if we take this term y transpose y, so this does not depend upon beta. Yeah, just like normal differentiation, this term would be 0. So we have 0. The next term, which is 2y transpose x beta. Now, for this y transpose x, you're going to get the transpose of this thing, right? So you're going to get twice of y transpose x transpose, which is y transpose x transpose. Okay. And for this thing, for this thing, you can remember a formula. Okay. Let me just write this formula for you guys. Del x of x transpose ax is equals to twice of ax transpose. Okay, now this is a formula for reference. Okay, this is a formula for reference. Now here x trans this a term, notice this a term. This a term is x transpose x, right? And this x term here is the beta term here. So we get twice of ax transpose, but let me write something. If um, A, if A, that matrix A is symmetric, if matrix A is symmetric, then sorry, then d dx of x transpose ax is actually twice of ax, twice of ax, right? So we are going to write twice of ax here because x transpose x is symmetric. So we're going to write plus of twice of ax, which is twice of a is x transpose x, a, and x is beta, beta. And now this term is 0. Right. Okay. Okay. Let me just separate this thing out. This is a separate topic. Okay. So this thing is 0. So what do we get? We get we can just cancel these twos. Oh, sorry. We can just cancel out these twos, and we get x transpose x beta is equals to y transpose x transpose y transpose x transpose. This transpose is going to be, you know, x transpose y. So we are multiplying with x transpose um, x inverse and with beta. Sorry, x transpose x with x transpose x and beta. And on the right hand side, we get again multiply x transpose x inverse with this thing is going to be x transpose y, right? So this term is, sorry man, what's happening? Yep, this term and this term is going to cancel out. So we get beta to be equals to x transpose x inverse x transpose y. Now here we get the final value of beta. This is the value of beta we were deriving. So beta becomes x transpose x inverse times x transpose y. Now, so this is the optimal value of beta. Now, what is beta? Beta will be giving our column matrix containing beta 0, beta 1 till beta n. Okay, so um, can I get back to my code? Can I get back to my code? All right, multiple linear regression. We're starting with multiple linear regression. Okay, let's import libraries. We are generating synthetic data x, y, right? Okay, so this is what our features look like. Feature 1, feature 2, feature 3, feature 4. We have 4 input features, right? And the data set has 200 values because we made 200 samples in the make regression class. Um, and there is just one target column. All right. Okay, we just plotted the data. Now, this does not show anything because this is a multi-dimensional data and we cannot plot this data because this data is actually 1, 2, 3, 4, 5, 5, and adding target would be 6 dimensional. So, yeah, so we cannot plot this data. Uh, so we just used a simple 2D plot. Okay, we are training the scikit-learn linear regression model. So this is the linear regression class implemented by scikit-learn, and we are training our model by creating an object of this class LR. We called LR.fit on X and Y, and we just predicted Y hat. Now Y hat is that column vector. So the intercept and the coefficient. Now what was the intercept? The intercept was the B naught value, I guess. B naught value was the intercept, and all of the values from B1 till Bn are the coefficient values, right? So these are the coefficients. We get 1, 2, 3, 4, 5 coefficients since there were 5 input columns. So we get 5 coefficients for all of them, and we just got one intercept value, right? Now we are going to implement our custom class. Just a second. Yeah, we're going to implement our custom class. This is our custom class. Um, okay, the custom class is named myMLR. We have a constructor at the beginning. The constructor just initiates the coefficient, the intercept, and the betas. The coefficient is all the coefficient terms, uh, all the coefficient terms starting from beta 1 till beta m. And the intercept is just the beta naught term. And self dot betas is that beta matrix which we use, that is a column vector. Okay. The fit method. The fit method takes in x, takes in y as two inputs, and x new np.concatenate. We get we just concatenate one because what was the x? I mean, our x was the x matrix x11, x12, x13, x21, x22, x23. But our x matrix has a column, the first column as 1. So we are just inserting np dot ones at the beginning column, at the first column, and we are concatenating it with the rest of the x values. So we are creating a new x matrix with the first column as ones, right? Um, then we have the y column. We are just shaping the y column to be of the size containing -1, 1. What is 1? This one, the right side 1. The right side 1 denotes it should have one column. And the left side -1 denotes -1 is for numpy to figure it out how many rows it will be. The left side is for rows, and -1 lets numpy figure out how many rows you have. So we have y column to be just a column vector. We have self dot beta. So now the self dot beta is actually that calculation which I said. Beta is x transpose x inverse x transpose y, which we just calculated. So we take x transpose, which is x new transpose times x. So this is x transpose x, and we are inverting it, right? So this is np dot linear algebra dot inverse x transpose x. Okay, and then we are multiplying it with x transpose y, which is x new transpose, and then y. Our y is y call. Okay, no issues with that. Okay, the first element. Okay, we just calculated the betas here, right? The betas would be np dot linear algebra dot inverse x transpose x, and then multiplying with x transpose y. The next thing, after that, we are calculating the intercept and the coefficient. These are the instance variables. I mean, we just created this so that we can print them out and see the values. So the intercept is actually the first beta. I mean, the beta matrix which we got here. This is going to be a column vector. So the first number, which is 0 cross 0, um, that is our intercept number. And the coefficient are all the betas from beta 1 till beta m. So we just slice it from the value of 1 to all the values, and we just flatten it because this was a column vector. We just flatten it to be just one dimensional numpy array. And the predict method, what does the predict method do? The predict method takes your x, concatenates first column as one, column of 1 to your x, and then calculate the y hat by multiplying x times beta, which was our y hat which we derived, and then returns the y hat in a flattened version as a 1D vector. So let's run our class, and we created a new object of our class, which is myLR. So let's run this. Okay, so we get the intercept to be 1.74. Okay, and the coefficients to be 23.57 and so on. So let us compare these models. So our intercept was 1.74, and the original linear regression class of scikit-learn has also given us 1.74. And the slope values, as we can see, are matching as well. Right, so this is again success. So we just implemented our own multiple linear regression class, sorry, from scratch using just Python and a bit of NumPy pandas as well. So I guess I'm clear with the simple and multiple linear regression. Uh, can I get back to the PPT? Right. So multiple linear regression, y equals to b naught plus b1 x1. We just did that, and we already know what b is. B is our beta, and x1, x2 are all the input features till xn. So we just created this line, and as you can see, these points, we are finding out the distance of this point from this plane. This is the residual error, which is the, and this point will have sorry, this point will have y1 value, and this point will also have a y1 hat value. So we are just finding out the difference between them and then squaring it up. This is the residual. We are finding the square of the residuals in our mean squared error function. So the cost function is again the same. This is the mean squared error function. So I've just copied the same slide again. But the thing is, we don't write the mean squared function for multiple linear regression like this. Instead, we write it in the matrix form, just as I showed you, which is E transpose E, small e transpose E. And yeah, but it's still the same. It's still the mean squared error function. So again, our goal in multiple linear regression as well is to minimize the mean squared error to find the optimal values of MNC, not MNC. Here it should be the optimal values of all the betas. Okay. Okay, so we are nearly at the end of our PPT, but we have one more thing for you guys, and that is going to be a small project, which is a mini project based on what we have learned so far. So the PPT ends here, I mean, nearly ends here. The summary is we have spoken about linear models. What are linear models? Models which try to identify or capture linear relationship in your data. So we have spoken about linear regression model. Um, Simple and multiple. So, okay, the math was all about y equals mx plus c for the simple linear regression and the matrix algebra for the multiple linear regression use. And when to use, we can use linear regression when you want to predict a continuous output variable, I mean output column. As we have spoken, regression is all about continuous output data like price, temperature, sales. Based on some input features, if you want to predict them, we use regression. So future topics in continuation. Um, if you all enjoyed the video, you can let us know, and we will continue with a lot of other interesting topics in future, connecting linear regression with a lot of other advanced features. So the future topics you can explore, or we can explore together as well, will be regularization, which is optimization technique to reduce the overfitting. I saw people discussing about overfitting. So this regularization is a technique for countering overfitting problems. Uh, we have ridge, lasso, elastic net, which is different regularization of different norms. And then optimization technique like gradient descent, we have used ordinary least square method, which is internally used by scikit-learn as well. Uh, and that is the reason our results were the same with scikit-learn's class. So there is another method known as the gradient descent method, which is a famous optimization technique in machine learning and deep learning. We can discuss them in another session. And then you can learn about perceptron, which is a very interesting algorithm and forms the base of neural networks. And logistic regression, which is nearly a simple advanced version of perceptron itself. So these are the future topics. You can refer to them, and we can also refer to them together. All right, before coming to this slide, let's continue to our mini project which we were speaking. So can I get my Google Colab notebook again? Okay, let me connect. Uh, Okay, so we have used a data set which is the advertising spend versus sales. This is the data set we are speaking about. We'll be leaving a link to this data set, and the data set is available on Kaggle. You can download it. I've downloaded the zip file, and the data set contains actually three input columns, which is how much the company has spent on TV, for these advertisements, for radio advertisements, and for newspaper advertisements, and what was the sale generated based on these inputs. So this is a good data set for practicing what we have learned so far. And the good thing about this mini project will be we are not using scikit-learn, we are using our own custom created class. Okay, so let me just upload um, to this ad versus sales. Ad versus sales is uploaded. Okay, let me just uh, run. Okay, we are unzipping this because we have zip file. So we are unzipping this. Okay, we got this CSV. And let's import this CSV. Okay, so this was our data, TV, radio, newspaper. These are the input features, and we have sales as the output feature. And so we can see the shape of this data. This has 200 columns and 200 rows and 4 columns. Out of that, the last column is going to be our output column. So we're going to separate the columns into X and Y. Okay, the X column will be taking all the rows value, and the columns, all the columns till the -1 column. That is the last column. So till the last column, that is till second last column, we'll be taking all the columns. So this is the X. We are seeing the X now. Yeah. So X we have TV, radio, newspaper, and for Y we just take all the rows and the last column. So we got Y as this. All right. Now train test split. Now I since I didn't explain about train test split, I just said I'll be explaining about train test split in the future. So train test split is that you split the data uh, into training and testing samples so that you fit your data on training samples and then you can analyze the performance of your model. I mean, you fit the model on your training sample and then you can analyze your model's performance on some unseen data which are kept reserved, which is known as the testing data. So you just separate out the data into two chunks. Let me say you have 10 samples. You just separate out 8 samples to be your training sample and 2 samples to be your testing sample. Right. So you'll train your model depending upon those 8 train samples, and then you test your model depending upon that 2 testing samples. Right. So this is train test split. So we have scikit-learn class for train test split. This is there in scikit-learn's model selection, and we are doing train test split, and we are separating out x into x train x test and y into y train y test. We just gave x and y, and we said the test size was 0.2. That is 20% of the data will be going for the testing data. uh, yeah, that's it. So now you can see explained shape is 160 because 20% we had 200 columns, 200 rows. So 20% of the data was 40. So 20% of the data went to testing X test and 160, which is the rest, went for training. Okay. So this was our custom machine learning, MLR class, which we just implemented in the previous notebook. I just called back the previous class, copied the previous class, and now let's fit our model. Okay, our model is MLR. We have created this object of our MLR class, and the intercept is coming out to be 2.7979, and the coefficients for the three attributes for the three value features are these. So, but the thing is, we have created our model, but we need to understand how well our model is performing, and for that, we calculate a very famous metrics used in regression tasks, that is the R2 score. Okay, the R2 score is a score which we generally print out, which we find in order to see how well our model is performing. Um, can I get back to my notebook? Okay, okay, I can get back to my notebook here. Okay, let me just explain what R2 score is all about a bit. We're nearly to the end of our session. So R2 score. What is the R2 score? R2 score is actually defined as 1 minus. Just a second. Yeah, where was I? The R2 score is 1 minus SS residual upon SS total. Now, S residual is the said residual sum of squares. And what is that? The residual sum of square is summation of yi minus yi hat square. Yeah. This is the residual sum of square. You take the summation from 1 to n. Okay. And the S is total. This is the total sum of squared. And this is described as summation going from 1 to n yi minus yi bar. This is not yi bar, this is y bar. Okay, so this is our total sum of square. Now, R2 score, R2 is actually 1 minus this thing, summation of yi minus yi cap squared divided by summation of yi minus yi bar squared. Right. The thing is, what can be the maximum value of R2 and the minimum value of R2? Now, for a model which is very basic, you can take y hat. You can take y hat to be mean of y, and for that case, you are just saying the output is always the mean. Okay, and for that case, R2 will be 0, right? Okay, and somewhere if this your y hat is predicting even poor than what a basic human can predict, that is a basic human would say, the output of this value, or for any given input, the output will be the mean of the outputs. This is the very basic thing which you can say. So if you do this, your R2 becomes 0. If your model is slightly better than this, so your R2 starts increasing. R2 starts increasing from 0. Okay, but if your model kind of fails to impress the user and gives even poor performance than just saying that the output is mean, that time, so if the R2 increases, if your model performs well, R2 becomes more than 0, which shows some positive improvement. And if the R2 decreases, you are performing even poorer than just predicting the mean, then the R2 becomes lesser than 0. This is very poor. This is very poor. And at max, the R2 can be 1. Okay. The R2 can be 1. For R2 to be 1, this right hand term should be this right hand term should be 0. But for this to be 0, for R2 to be 1, what we need is summation of yi minus yi cap squared to be 0. And this is the case someone was speaking about in the comments, that is a perfect model which makes no error. And for a perfect model, the R2 is 1. So for good models, R2 goes from 0 to 1. And the closer you are to 1, the better you are doing in predicting the output. Okay, so let's go back to our code. So our code found out the R2 to be 0.89, which is nearly 90, nearly 0.9. Okay, so our model is performing really well. Now we can improve the performance by doing some optimizations like regularization and all. But regularization would not be that much effective. I don't think so, because the coefficients are nearly 0. All right, we will see it in some future sessions. So let me just plot the uh, this is the regression line, which is plotted in a 2D manner. It should not be 2D, it is actually a hyperplane, but yeah, you can observe it in 2D. This is the line which we plotted. So yeah, this was our mini project, and I hope you guys enjoyed doing simple linear, multiple linear, and then finally a project which is really good because you implemented all of the classes on your own. So this is really good. So I guess we are on to the end of our session. What's the time? It's 7:52. We are perfectly on time. So if there's any questions, I would like you all to ask. I mean, I'm getting a very poor view count, man. I don't know. Was I that bad? I don't know. Yes, please. Yeah. Why is so less people watching? Okay. So let me move to my PPT. Um, this is the um, my Linktree QR. You can connect, or you can connect with me, and you can ask me your questions if you have. I'm always available to answer questions, and I don't get any questions, so I think so we can end. Is Moidoya here?